In this video, we're solving problem 8.3.506.XP.MI from the Larson and Edwards Calculus, Early Transcendental Functions text, 7th edition. We're asked to find the integral involving secant and tangent. And it's the indefinite integral of tangent squared of 2x times secant to the fourth of 2x dx. Now, since I've got powers of secant and tangent, the first thing that I would do is I would use the appropriate rule for this. Notice that the power of tangent is even and positive, and the power of secant is even and positive. So I'm going to show you where to find this on our Blackboard site. So I'll share my screen with you. This is what it looks like on our Blackboard site. If you go to announcements, once you log in, you're going to see this. If you go to Unit 1, Advanced Antidifferentiation Techniques, you'll see this over here. And then you're going to scroll down. And remember, these are all of our lessons. And lesson 4 for Unit 1 is right here, trigonometric substitution. You've got your notes. You've got your practice problems. You've got a printable version of the lesson plan, if you're a hard copy kind of person. Now, if you scroll down a little bit further, it shows you will be provided with the attached formula sheet during the first exam and during the final. So I want you to click there. And this is a summary. Oops, I'm using the wrong one. I went to trig substitution. Sorry about that. That's true. That's the right formula sheet for trig substitution, but we're in the trig integrals section. So I want to go to Unit 1, Lesson 3. There we go. Same thing. Scroll down. This is the formula sheet that you'll have during Unit 1 exam for trigonometric integrals. So it tells you everything that you're supposed to do. You don't have to memorize this. You can use this as a reference. It's a 2-page summary. It doesn't have all the examples that the notes have, but it gives you the guidelines. And we're looking at, look at this, tangent squared of a constant times x times secant to the fourth of a constant times x. We've got powers of sine and cosine, those guidelines there. Powers of secant and tangent over here. And now I want to look through these guidelines. We got 6 of them. And we want to see which one applies. It says, if the power of secant is even and positive, you're going to make the substitution, let u equal tangent of kx. Okay, so it tells us exactly where to start. When you're working these problems, if you don't know where to start, look at that formula sheet. It's going to tell you exactly what to do. You'll have access to that during your exams if you're taking my class. And so we say power of secant is even and positive. Let's let u equal kx, where k is whatever that angle is, or that constant is. So we're going to let u equal tangent of 2x. Now, if you read those guidelines further, it would say save a secant squared factor for du. So we let u equal tangent of 2x. And then we compute du. The derivative of tangent of 2x is secant squared of 2x times the derivative of the inside by the chain rule. So we get an extra 2 there. Don't forget your dx for your du. And we want to save one of these secants, or 2 of these secants. You've got secant to the fourth, so that's secant times secant times secant times secant. Did I say all 4 of them times secant? I want to save 2 of them for my du, and then everything else I want to write off to the side. So, and that's what the guidelines say as well. So I'll have tangent squared of 2x here. If I've got 4 secants, I want to leave 2 of them over here and factor out 2 of them for my du. So that's our first step. We let u equal tangent because of our guidelines. We compute du. And then we factor out that secant squared of kx. In this case, it's 2x for du, for a du factor. Okay. And it turns out that secant squared of 2x dx isn't exactly du. So I'll solve this equation for secant squared by dividing both sides by 2 or multiplying by 1/2, same thing. And now my goal is to write everything here entirely in terms of u. This is 1/2 du because of what we just did there. Those are the same thing if I make that substitution. If u is tangent of 2x, this is just u squared. Now I also have a secant squared of 2x left, and I need to write that in terms of tangent as well. Now whenever you're working with powers of tangent and secant, or not whenever, but often when we're working with powers of tangent and secant, this identity comes up. If we take our Pythagorean identity for sine and cosine, sine squared of an angle plus cosine squared of an angle equals 1, and then we divide it by cosine squared, we get tangent squared of an angle plus 1 equals secant squared of the same angle. So this is the identity that we can use to write even powers of secant entirely in terms of tangent. Now we could do that with odd powers of secant as well, but we'd end up with square roots and we don't want that. But this is what the guideline said. It said, if the power of secant is even and non-negative, well, it's going to be even and positive actually, factor out that secant squared for du and write everything else over here in terms of tangent. So I've got this in terms of tangent already, and secant squared, I need to write that in terms of tangent. And then this secant squared, I don't want to write this piece in terms of tangent, that's for my du. Everything else in the brackets needs to be written in terms of u. Well, I can do that because of this identity. Since tangent squared of an angle plus 1 is the same as secant squared of that angle, this secant squared of 2x is the same as tangent squared of 2x plus 1. And tangent squared is just u squared, so that's u squared plus 1. Don't forget your parentheses because you've got two terms there that are being multiplied by that tangent squared. All right, so we factored out our secant squared for our du, and then we've prepared to write everything entirely in terms of u. And in order to do that, we had to use that trigonometric identity that secant squared of an angle is 1 plus tangent squared of the same angle. And now we're here. I've got u squared times u squared plus 1 multiplied by a 1/2 and a du. Now it's very tempting to just anti-differentiate that piece and give me u cubed over 3, and anti-differentiate that piece and give me u cubed over 3 plus u. Don't do that. You've got a product here. There is no product rule for antiderivatives. So what you have to do instead is you have to distribute that u squared, and then you can use the power rule. I would also factor that 1/2 out front. So I've got 1/2 of u squared times u squared, add the exponents, that's going to be u to the 4th. And then u squared times 1 is u squared. We're multiplying all of that by du. So we wrote the integral in terms of u, then we distribute. And now we just use the power rule, easy breezy. So you add 1 to the exponent, and you divide by the new exponent. Over here, same thing, add 1 to the exponent, and divide by the new exponent. Don't forget to add your constant of integration. Isn't that nice? Through making a u substitution, using our trigonometric integrals guidelines, just turn this problem into a power rule problem. Easy breezy. Now, the last thing we need to do is distribute that 1/2 and then, of course, back substitute. I'm just leaving space for those trig functions. Remember what u was. That was tangent of 2x. So I've got tangent of 2x raised to the 5th, or tangent to the 5th of 2x. And then tangent of 2x quantity cubed, so that's tangent cubed of 2x plus c. So we're just back substituting, which is the same as just replacing u with whatever it was in terms of x. In this case, it happened to be tangent of 2x. And that's our answer. If you take the derivative of this, you're probably not going to get exactly this the first time. But if you take the derivative of this and you apply this trig identity, I'm confident that if you take the derivative of this and apply this identity, you can rewrite that result in this form. And that's what this is. An antiderivative is a function that you can take the derivative of that will give you this function back. It might not happen directly, but with trig identities, we could prove that that was true, or that is true, excuse me.